Okay, in this video we're going to flip things around a little bit from the standard computation of a confidence interval, and we're going to ask instead, for a given width of a confidence interval, how many trials do I need to perform? So this is a similar problem to the last video, and it says a test item is piloted for inclusion in a standardized exam. A 95% confidence interval is created for P. How many takers should respond to the item so that the length of the confidence interval is approximately 0.05? And it tells us to use 0.4583 as the estimate for sigma. And one thing I forgot to type in this problem was that P is the probability that a randomly chosen test taker responds correctly to the item, just as in the last video. And this number right here, I'm going to explain how I arrived at that, just to give you a sense of how you might do that. The standard deviation for a Bernoulli random variable is p times 1 minus p. So I'll say, well, the average is about 70%. You know, I'd say I try to gauge test questions so that the ideal class would have probably about 70% of them answering that one entirely correctly. Okay, so I took the square root of 0.7 times, 0.3, and it's about equal to that decimal. So that number didn't just come out of nowhere. Now, why would we want this? Well, if we look in the last video, I'm going to pull up the very bottom in the last video. Here we computed the confidence interval, and we arrived at this confidence interval. This is rather wide, right? The probability of a randomly chosen test taker responding to this item correctly can range from about 0.58 to about 0.75. That's our 95% confidence interval. The width of that interval is about 0.17. Yeah, it's about 0.17, 17%. There's a 17 absolute percent. This isn't real, not like 17% of the estimate, but a 17 percentage point range in which that confidence interval lies. That's actually a pretty wide range. So when you're designing a statistical study or an experimental test, it's good to have these kind of things in mind. How precise of a result do we want at the end? Because how precise of a result do we want at the end is going to affect how many trials we need to do, or how big our sample size is. Here, how many students we need to respond to the test item to give us the estimate. Okay, so let's draw our picture here. So what's going to happen is we'll have a Bernoulli random variable. That's 1 if the student responds correctly, 0 if the student does not respond correctly. We'll include omissions into that incorrect region. Okay. And then we're going to have x1, x2, all the way out to xn. And our goal is to figure out what that n should be. Once we do that, we compute x bar. And x bar is just, well, it's the sum of the xi's over n, right? Because it only contributes 1 to the sum if the person got it correct. Okay. And then according to the central limit theorem, so long as n is large and the observations are independent and identically distributed, then this is going to be approximately normal with mean p and standard deviation. Let's see, what do we say to assume? 0.4583 divided by the square root of n. Okay, so we'll have our normal distribution here. And of course, we don't know what the mean is. That's what the end result of this kind of a study is trying to estimate. Instead, what we know is a sample mean that we saw. So we'd have z sub x bar, take the absolute value, minus z sub x bar, take the absolute value. Okay, and this area is the probability that a sample mean is no more extreme than what we saw, that it's no further from the actual mean than what we saw happen. Okay. We want, for a 95% confidence interval, this area to be less than 0.95. So we look up the absolute value of that z-score on a table, and that gives us some area A. Now, but that area A is also including this tail over here, and the size of this tail, the area of this tail over here, is 1 minus a, because a is giving you the area all the way to the left from this line. So the area out to the right is 1 minus a, since the total area is 1, and this area on the right side is equivalent to this area on the left side. So to get just this portion, this symmetric part of the bell curve that stops right here, we would take a and subtract 1 minus a, and we want that to be less than or equal to 0.95. Okay, so we saw before that you go through this inequality and we get a is less than or equal to 0.975, and that means that our z-score, if we look that up on the table, see that's right here, 1.9 and then 0.06, so that's 1.96. So z-score needs to be less than or equal to 1.96. Okay, I know I flew through that, but the reason is this is the same, pretty much the same calculation as what we did in the previous video. And now it's going to get just a little bit different, though not a lot. Okay, so what is our z-score? Well, we have negative 0.196 less than or equal to, whatever that z-score is, less than or equal to 1.96. The z-score is x bar minus the actual mean p divided by, let's see, this, the standard deviation of the normal distribution for x bar. So we've got 0.4583 divided by the square root of n. Okay, and we want that the length of the confidence interval is approximately 0.05. So we're going to go ahead and act like we're finding this confidence interval, and to find the confidence interval we solve for p. So I multiply both sides by this denominator, and since it's positive I don't have to change the sign, and we get 1.96 times 0.4583 over square root of n is less than or equal to x bar minus p, which is less than or equal to 1.96 times 0.4583 over the square root of n. Okay, so we subtract x bar and then multiply everything by -1, and this would become, let's see, x bar plus 1.96 times 0.4583 over the square root of n greater than or equal to p greater than or equal to, let's see, we'll have x bar minus that over here. So we're going from x bar plus this value to x bar minus this value, or if I guess we go from left to right on the number line, we're going from x bar minus this value to x bar plus this value. That implies that the length of the confidence interval is the difference between those. It's x bar plus 1.96 times, put a dot there because it's traditional that if you put a fraction right beside a number, then that means addition. And the strange thing is, if that's if this is instead of variable, then it means multiplication, but we won't go into that. Okay, and we subtract these two endpoints to figure out how wide or how long the confidence interval is. Okay, the x bars end up canceling, and I got a minus, so that gives me a plus, and I end up with 2 times 1.96 times 0.4583 over square root of n. And we want this, so we want equal to 0.05. So let's do that. Let's set it equal to 0.05 and solve for n. So we have, let's see, I'll go ahead and multiply this out. 2 times 2 is 4. I got a 0.04, so multiply that by 2, I got 0.08. So take 4 minus 0.08. and we end up with 3.92 times 0.4583 over the square root of n. We want that equal to 0.05. Okay, so the square root of n is, let's see, 3.96 times 0.4583. I'm holding out till the end to use my calculator here. Divide by 0.05, and that's the square root of n. And of course, that's the best way to do it because you don't have compounding rounding errors. At least anything beyond the rounding that the calculator has to do. Although, as I say that, I'm sort of being a hypocrite because I went ahead and rounded this value instead of using the square root of 0.21. Okay, so that's the square root of n. So of course, n itself is just going to be the square of this. So we have 3.96 times 0.4583 divided by 0.05 squared. So if I pull up my calculator, let's see here. I have 3.96 times 0.4583 divided by 0.05, and then square that. Okay, so, whoops, lost it. We get about 1317. So our sample size needs to be about 1317 or 1318. If we strictly rounded, then it'd be 1317. If we wanted a length absolutely no larger than 0.05, then, well, you could make a case for 1318, but yet you can't really deal in absolutes here because we sort of just pulled this out of the blue estimate for the standard deviation. So this is a ballpark estimate, right? It might as well round to the nearest value. Okay, and we get 1317. Oh, whoops! And I look down to my my notes here, and I have a different value. And you guys probably picked up the mistake. I made a mistake here, and that is, I think I said 3.92, but I wrote down 3.96. That should have been a 2 there. So let's pull up our calculator. That's not right. That's not right. That's not right. And let's see, I don't use this calculator very often. I don't know if I can pull up what I just had here or not. Nope, I don't think I can, so I'm just going to enter it again. So I have 3.92 times 0.4583 divided by 0.05. Then we square that. And there we go, we get 1291. Okay, so that should be 1291. Okay, sorry about that. So, in order to get a confidence interval for this probability of a randomly chosen test taker responding to the item correctly, in order for that confidence interval to have a length of about 0.05, we're going to need a sample size of somewhere around 1,300 test takers. We need a large sample size. And the reason for that is that we have a Bernoulli random variable, and it really doesn't give us that much information. It just gives us a yes or a no. And that by itself is not a very good estimate for the mean, so we need a bunch of those measurements to get a good estimate for the mean of that distribution. Okay, so this is an example of something that's actually pretty useful in practice, and that is before I do an experimental study, do the analysis of what's going to happen, what the end result's going to be, to see how large I want my sample size to be to get the kind of results that I'm hoping to get. Okay, I'll see you in the next video where we'll talk about a t-test example.